Okay, in this video we are going to solve a linear second order ordinary differential equation using the Laplace transform. So we have this second order linear ordinary differential equation which is of one variable. So at the end of the day I just have to find the function u of t. By definition, the Laplace transform of the function u of t is equal to the integral from 0 to infinity u of t times the exponential minus t dt. Okay, so from my t domain I go to the s domain. So this is as denoted as capital U of s equal from 0 to infinity u of t times the exponential to the minus t dt. Okay, what I have to do now, I have to compute the Laplace transform of this constant function on the right hand side, the Laplace transform of u of t, u prime of t, and u double prime of t. Of course, I start to compute the Laplace transform of 5, which is equal from 0 to infinity integral 5 times my exponential dt. 5 is just a constant. It can be pulled outside from the integral, so it's 5 times the integral from 0 to infinity e to the minus t dt. So it's 5 times e to the minus t over minus s. So if I take this derivative, I get this function. So it's from 0 to infinity. So it's minus 5 over s times the limit of t going to infinity e to the minus t minus limit of t going to 0 e to minus st. So this is minus 5 over s times. As t grows, this is the exponentially decaying to 0. So it should be 0 minus e to the power of minus s times 0 is equal to 1. So at the end of the day is 5 over s. This is my Laplace transform. Now, of course, the Laplace of u of t is just equal to the integral from 0 to infinity u of t e to the minus t s times t dt. So it's capital U of s. Now I compute the Laplace transform of the first derivative, which should be the integral from 0 to infinity u prime of t times e to the minus st dt. What I do here is just integration by parts, so I have u of t times the exponential from 0 to infinity minus integral from 0 to infinity u of t times e to the minus t derivative dt. So here I just let's start from this integral term here. So the derivative of s, this is minus s times the exponential. The minus s will go outside and it will change sign with a minus, so it should be s, the integral of 0 of t, 0 from 0 to infinity u of t times e to the minus s t dt plus the limit of t going to infinity u of t times e to the minus st minus the limit of t going to 0 u of t e to the minus st. This is just s times capital U of s plus this term goes to 0 as t grows to infinity, and this term is just minus u of t, so it's minus u of 0, sorry. So it's s times capital U of s minus u of 0. So u of 0 from my initial data is equal to 0. So in the end of the day, I just have s times u of s. Okay, now I have to go, it's simple to do the calculations, they are pretty straightforward. Now I have to go to find the Laplace transform of the second derivative of u. The Laplace transform is from 0 to infinity u double prime of t e to the minus st dt. I do again the integration by parts. Minus integral from 0 to infinity u prime of t times e to the minus st derivative dt. So this again is s times the integral from 0 to infinity u prime of t e to the minus st dt plus the limit of t going to infinity u prime of t e to the minus st minus lim t going to 0 of u prime of t e to the minus st. Of course, this goes to 0 as t growing to infinity. This is minus u prime of 0, so it should be s times, this is the Laplace transform of the first derivative, which is s u of s, pre-computed. We have computed this from the previous step, and it is minus u prime of 0, and u prime of 0 is equal to 0 from the initial data that we have for our ODE, for the initial condition. So it's s squared times u of s. So going back to the ODE, it's u double prime plus 3u prime of t plus 2u of t is equal to 5. I take the Laplace transform on both sides, so it is a linear integral transform, so it should be Laplace u double prime of t plus 3 times Laplace transform of u prime plus 2 Laplace transform u of t is equal to the Laplace transform of 5. So this is s squared capital U of s plus 3 times s u of s plus 2 times u of s equal to 5 over s. I take u capital U of s to be the common factor, and inside I have s squared plus 3s plus 2 is equal to 5 over s. I solve with respect to capital U, and this gives 5 over s times s squared plus 3s plus 2. So it is u of s equals to 5 over s squared plus 3s plus 2. Okay, so I have to break this into partial fractions. So I have a over s plus b over s minus s plus c over s minus. Okay, this s squared plus 3s plus 2 is a quadratic function. Okay, it's a polynomial of degree 2. So I can find the roots of this. So this is, I compute the discriminant, it's 9 minus 8 equal to 1. So s plus is minus 3 plus the square root of the discriminant over 2 minus 2 over 2 is equal to minus 1. And s minus is minus 3 minus 1 over 2, so it's minus 4 over 2 minus 2. So this can be written as alpha a over s plus b over s, s minus s plus, s minus s plus is equal to s plus 1 plus c over s plus 2. Now what I have to do is I have to find these coefficients A, B and C, okay? So I go here and I multiply with multiply both sides by s times s plus 1, s plus 2. Okay, so it should be 5 is equal to a times s plus 1, s plus 2 plus b times s, s plus 2 plus c times s, s plus 1 is a times s squared plus 2s plus s plus 2 plus b s squared plus 2s plus c s squared plus s. I have to do some calculations here. So this should be as squared plus 3as plus 2a plus bs squared plus 2bs plus c times s squared plus c times s. Now I have to group my terms, so I just group the terms that are associated to s squared. So it's this term and this and this, so a plus b plus c plus the terms associated to s to the power of 1 is this term and this term and this term, so it's 3a plus 2b plus c plus this constant term 2a. So from here I have to compute these constants a, b and c. So from here what I see is that on the right hand side I have the s squared, but here on the left hand side I don't have any s squared. So this alpha plus b plus c should be equal to 0. A plus b plus c is equal to 0. Also the terms associated to s are non-existent on the left hand side. So these three, in addition, 3a plus 2b plus c is equal to 0. And last but not least, 2a is equal to 5, so a is equal to 5 over 2. I substitute a here, so b plus c is equal to minus a, equal to minus 5 over 2. And 2b plus c is equal to minus 2b plus c is equal to minus 3 times a. So it's minus 15 over 2. So I have b plus c is equal to minus 5 over 2, and 2b plus c is equal to minus 15 over 2. I do a subtraction, so 2b plus c minus b plus c is equal to b equal to minus 15 over 2 minus 5 over 2 plus 5 over 2 is minus 10 over 2 minus 5. So b is equal to minus 5. Now let's choose one relation to substitute in order to find c. So I have my a, okay, I have my b. Now I just have to compute the c. So c is equal to minus, I use this relation, minus b minus 5 over 2. So it's 5 minus 5 over 2 is equal to 5 over 2. There you go. I also have my C. Okay, so A is 5 over 2, B minus 5, and C 5 over 2. So now that I have my constants A, B, and C, I can write that U, capital U of S, is equal to 5 over the A was 5 over 2, so 5 over 2 over S plus B is equal to minus 5 over S plus 1, and the C plus 5 over 2 S plus 2. This is what I have. I rewrite this 5 over 2 times 1 over S minus 5 over S plus 1 plus 5 over 2 times 1 over S plus 2. Now, in order to find my solution, I just have to take the inverse Laplace transform of U of S. So the inverse of this gives me my U of t. So I take, it's a linear, the inverse transform is a linear transform, so it's the Laplace, inverse Laplace of 1 times S 5 over 2 minus 5 times Laplace inverse 1 over S plus 1 plus 5 over 2 times inverse Laplace transform 1 over S plus 2. Consequently, this I have to find the function that when I take the Laplace transform gives me 1 over S. This is just simply 1, so the inverse, it should be 1 minus 5 times. Here I have the inverse Laplace transform of 1 over S plus 1. I have to find a function that gives me the Laplace transform is equal to this quantity over here. So this is just the exponential. So it's 5e to the minus t plus 5 over 2 e to the minus 2t. So u of t is equal to 5 over 2 minus 5 times e to minus t plus 5 over 2 e to minus 2t. Let's see, we can do a simple test to verify that this is our solution. Okay, so let's check the initial conditions. U of 0 is equal to 5 over 2 minus 5 e to 0 to the power of 0 plus 5 over 2 e to the power of 0. So it's this is 5 over 2 plus 5 over 2. 10 over 2 is equal to 5. Minus 5 is equal to 0. Let's compute the derivative of u of t. It should be 5 times e to the minus t minus 5 e to the minus 2t. So u prime of 0 is 5. 5 minus 5 is equal to 0. Another thing that you can do is take the solution. It's not necessary, but you can check, take this solution and see if this function satisfies your second order ordinary differential equation. So check if this u double prime of t plus 3 u prime of t plus 2 times u of t is equal to 5. Let's do the calculations. So let's compute. Okay, the second derivative should be minus 5 e to the minus t plus 10 e to the minus 2t. Okay, so I just substitute this is 5 e to the minus t plus 10 e to the minus 2t plus 3. The u prime is 5 e to the minus t minus 5 e to the minus 2t plus 2 times the u of t is 5 over 2 minus 5 e to the minus t plus 5 over 2 the minus 2t. I just do the calculations. Okay, so I have 5 plus, let's group the terms that are associated to the e to the minus t. So it's minus 10 is this one, this term, and this term, and this term. So minus 10, minus 15 plus, minus 10 minus 10 minus 5 plus 15 plus e to the minus 2t. It's this term, and this term. So it's 10 plus 5 minus 15. So it is, this is minus 15 plus 15, this is 0. 15 minus 15, this is 0, so it's equal to 5. So my solution finally is, it is correct for this initial data that I have. This is my solution of my ODE, ordinary differential equation. And also for this, you can also find what is the behavior of the function as t goes to infinity. Let's see, let's take the limit as t grows to infinity. It's just the limit so just the exponentially decaying functions as t grows go to 0. So it's 5 over 2. So the u of t goes to 5 over 2 as t goes to infinity. Okay, so this was my this was the basic example of solving ordinary differential equations. It's a very suitable tool, Laplace transform, to solve this this type of ordinary differential equations, because you just go from the derivatives, you go to something very simple. Algebraically, you just solve with respect to the function u of s, and then you just have to find these coefficients and take the inverse transform to find the function. So first you just find the first what you have to do is find these transforms here. So I have computed for the constant function associated to the right hand side, and of course I have u prime f u double prime, so I have to compute these Laplace transforms. Okay, it's very straightforward. Then you see that I just have this u of s. Now this is my unknown. I have to do this splitting into partial fractions, okay, and find these coefficients, then take the inverse on this equation, the inverse of the Laplace transform, and finally find my function. In order to verify that this is my solution, I can check the initial conditions and also can substitute back to the ODE and see if this is satisfied for this particular solution. Okay, and I can check that this solution stays bounded as the p grows. This was a basic example. Of course, Laplace transform is a very useful transform to solve ODEs. Also, it's very commonly used in signals and systems because when you take the Laplace transform, you just have transfer functions. It's used by engineers, by everyone. I hope that this video was useful for you. If you like this video or you have any request, please let me know. There are going to be plenty of videos following up, but this was just an initial video, and soon there are going to be more videos. Thank you for your time, and I hope that you are doing well.